All right, now let's look at a bunch of examples from the textbook and go over the hypothesis tests and see how we can reject or fail to reject those hypotheses that you're testing, right? So imagine here's a question. We're working with our wage equation. We're regressing log wage on education, experience, and tenure. And these are the numbers. The numbers are coming out of our output, right? Or any other kind of software. And we are interested to testing this. We want to test whether after controlling for education and tenure, after controlling for where is education and tenure, if higher work experience leads to higher hourly wages, right? So this is what we are interested. Whatever you're interested, you put it in alternative, right? So put it in alternative. So what is your H1 or alternative? It's going to be if this coefficient, so let's say this is beta 0, this is beta education, this is beta experience, this is beta tenure, right? We want to see if beta experience is greater than 0 or not. Again, whatever you want to show, you put it in alternative. And in the null, it's going to go, the rest of it is going to go into null. So again, if you write it like this, or beta experience less than or equal to 0, this is also fine. Okay, so one would either expect a positive effect of experience on hourly wage or no effect at all. So this is what we're testing. So imagine you see the numbers, right? So these are the numbers that you get out of the regression. And if you only look at, so here is a very subtle point, guys, that I want you to pay very good attention. So let me use another color. You know, I have a bunch of variables in the data set: wage, education, experience, tenure. I run regression, and the regression is giving me back these numbers: 0.022, 0.0041, 0.092, and etc., right? And I can go ahead and interpret that. So if I say if education increased by 1 unit, then wage is going to increase by 9.2%. Remember, this is log level. If experience increased by 1 unit, then the wage is going to increase by 0.4%. If tenure increased by 1 unit, then the wage is going to increase by 2.2%, right? So in this sample, be careful, in this one sample that we're using, it is obvious that your beta hat experience is equal to 0.0041, and it is greater than 0. So in this one sample, the effective experience on wage was positive, controlling for tenure and education. The question that you're interested, however, is what about the entire population? Yes, in this sample that was the case. But what about the entire population? Can I make this a statement for the entire population? So this is our original goal, right? And initially we said that how can you say about the relationship in the entire population? Now you have to construct some test statistic out of this number and say that, okay, if I can use that test statistic to make a judgment on the relationship between experience on wage in the entire population. So that's the goal. So that's why in the null and hypothesis, we don't put a hat on top of it, because it is nonsense. In the multiple choice question, I'll ask you this question maybe, that what is the right version of a null hypothesis, and these are the answers. So for instance, beta hat 1 is equal to 0, let's say null, yeah. Beta 1 is equal to 0, and etc. So this is absolutely wrong, because beta hats are observable. You can definitely observe what is the beta hat of experience here. We know that it's 0.0041. So what we test is if in the entire population the beta is positive or not. Right? So this is a very subtle point. Okay. So for that, we need to construct a test statistic. I assume that you have zero background in the statistic, and I want to use your intuition. I want you to think about it. How do I know for a fact that the effective experience on wage is going to be positive in the entire population? In the sample, yes, it was positive. It was 0.4%, right? In the entire population, how can I do that? I want you to think about it. Let's construct this test statistic together. For now, I just call it PJ, right? You can call it anything. You call it your initial. This is a test of statistic. I want to come up with a mathematical formula to test if experience is relevant, has a positive effect on wage in the entire population. So how about I go like this? I want to see that if this, at the end of the day, if this thing that I'm calculating minus 0, where is the 0 coming from? Because we're assuming that the null, in the null it's 0. So let's focus on this one. If this number, beta hat of experience minus 0, if this number is very large, is it good or bad? So if very large. Again, the goal is to construct this test of statistic. We're going to give it a proper name at the end of the day, but let's start with PJ. If very large, I want you to think about it. Are you happy or sad? So, and what do I mean by happy? Happy means that, yes, beta hat was too large. It means that there's a good chance that in the sample it was too large. So in the population, the effect is going to be positive. You don't know the exact number. Maybe it's smaller or larger than the sample, but it is positive. So imagine if this number, let me just exaggerate here. If this number was 1 instead of 0.004, you would feel a lot more comfortable to say that, okay, in the population, experience is positively correlated with wage, compared to a case that the number is 0.0000001. Does it make sense? So this number itself is important to us. The larger that number, the easier you reject the null. Is everyone with me? The larger this number, the easier I can reject that the experience is equal to 0, because it is farther and farther away from your null hypothesis. But is it good enough? So for example, let's say I have, my beta hat 1 is equal to 0.001. You might think that, okay, this is a very small number. So how do I know that this is in the entire population, beta 1 is positive or not? This is not enough. I need to give you more information. I need to give you the standard error as well. If I tell you that the standard error is going to be 0.0000001, then you are super happy. Because why? Because even if you look at the 3 standard deviation from this number, you are way above 0, right? So for that reason, we have to take into account the standard error as well. So that's why we are going to divide it by standard error of beta hat experience. So this is a statistics that intuitively makes sense. If this statistic is large, if this PJ statistic is large, you're happy. Happy means that you reject the null. Reject the null means that you get what you wanted, and you put what you wanted in the alternative. So you get, oops, sorry. Let me see, how can I fix this? Oops. So you get the alternative. You get the alternative. Does that make sense? So we come up with the intuitive statistic, test a statistic, and we said that it has something to do with how far we are from this number divided by standard deviation. Why do I need to divide it by standard deviation? Because I always think of this example. 0.001 seems to be very small and very close to 0, but if the standard error is 0.0000001, then you're way more comfortable to say that, you know what, if I do another sampling, in the new sample it's going to be greater than 0. And in the entire population, there's a good chance that it's going to be greater than 0, right? We're going to go ahead and replace this PJ. We give it a proper name. We call it T-stat. Or sometimes people call it T-ratio, right? So, and then we have to say if this T-stat is large or not, large enough or not. So in short, let me use another color. Let's use green. If this T-stat is large, very large, you are happy. You reject the null, you get what you want in the alternative. Now our next job is to define what is this large. What do you mean by large? Can you quantify that number for me? And I'm going to tell you that that large depends on your significance level, on your tolerance level as a researcher, okay? So we're gonna see that, for instance, if you're conservative and your tolerance level is 1%, that number is going to be, this T-stat is going to be greater than some threshold. if you're less conservative and your, let's say, significance level or tolerance level is 10%, then your t-stat is going to be greater than another threshold, right? So in the next slide, we're going to talk about those things. But I hope that you get what we're doing here in this example. So the goal is to come up with some rejection rules. So what is t? If t is greater than what, then I can reject the null. So for that, I need to back out a little bit and talk about the general cases, and we will get back to this equation, to this example. So in the next slide, let's look at the general version, and then we will come back to this example. Okay, so this is a t statistic that we constructed together, right? So initially we call it PJ, but now we give it a more proper name. We call it t-stat. T-stat of one coefficient, right? So t-stat of beta hat j. Again, you can simply call it t-stat. You don't need to write beta hat j. But t-stat for what variable, for what coefficient, right? So the null hypothesis, if the null hypothesis is beta is equal to 0, and what are we doing? We are saying that the population parameter is equal to 0 after controlling for all other explanatory variables. We say there is no effect of xj on y, right? The t statistic will be used to test the above null hypothesis. The farther the estimated coefficient is away from 0, the less likely it is that the null hypothesis holds, right? Again, the larger this t-stat, the happier we are. We can easily reject the null. But what does far away mean? Far away from 0. So we're quantifying that number. This depends on the variability of the estimated coefficients and the standard deviation. So we talked about it, why it depends on the standard deviation. Now the goal is to define a rejection rule so that if it is true, H null is rejected. So first case, we're going to start with one-sided example. So one-sided is, if we look at the alternative, if you want to say that the test is one-sided or two-sided. Let me see, we had it somewhere here, one-sided, two-sided. Yeah, here it was. No, I guess. I think we talked about this one-sided, two-sided. Yeah, here. So for example, this one example of the one-sided test, this was an example of two-sided test. I look at the alternative. Look at the alternative and decide if it is one-sided, two-sided. Okay. Now we're going to start with the right tail or right side test. So testing against one-sided alternative. Let's start with greater than 0. To imagine, I want to test if beta j is greater than 0 against beta j less than or equal to 0. Again, these are, we can use them interchangeably. It really doesn't matter. Okay. We are going to reject the null hypothesis in favor of the alternative. This is what we want, right? If t is too large, if your test statistic is too large, right? Larger than a critical value. So what is that critical value? Again, I told you that we have to compare it with what number, and that number comes from a threshold. The threshold comes from your tolerance level. As a researcher, your significance level. Imagine your significance level is 5%. You are okay to misdiagnose 5 of those gentlemen to be pregnant. Okay. So again, this depends on the field that you're dealing with. If it is, for example, COVID related, you want to minimize the false negative, not false positive. But again, that's a separate topic. Let's say here your tolerance level is 5%. If the tolerance level is 5%, you can go ahead and calculate the corresponding t-value, because remember guys, this has a t-distribution. We showed that, beta hat j minus beta j divided by a standard error of beta hat j has a t-distribution, right? Then if I tell you that my tolerance level is 5%, so I tell you that this shaded area is 5%, I can go ahead and calculate the critical value. So the sequence is like this. What is alpha? Then from alpha you calculate your critical value. We show it with C. And then from critical value, and then you compute, simultaneously you can compute your t-stat. And then you compare, these are the steps. You compare t-stat with your critical value. if t-stat, if your test is right tail and if t-stat is greater than critical value, good news, you reject the null because it was greater than your threshold, than your tolerance level. Okay, that's good news. We were far away from the point that we misdiagnosed 5 people. Let me use another color and give you another example. Let's say I'm more conservative. I'm more conservative, my significance level is 1%. Now, the corresponding critical value, let me call it C prime, is C prime, right? Now, if my t is large enough, if I calculate t and if it is here, it's good news, I can reject it. But if it is not, I cannot reject it. So you see, again, depending on your significance level, you compared your t-stat with C or C prime in this example. If it is large enough, we are happy, reject it. So that's why we call this area rejection area. This is our rejection area. If your t-stat at the end of the day you calculate, if it lies here or here or here or here, as long as it is greater than the threshold, we're happy. Now, we know how to calculate t. We will set up alpha. So the next job, how do you calculate this c? We are going to do it like this. How do you calculate the critical value? So if I tell you that this distribution is t distribution, and if I also give you that the shaded area is 5%, you can go ahead and calculate the area under the curve, right? So I know that the CDF of my critical value is 1 minus alpha. Does this make sense? What is CDF? So the CDF of the critical value. So if this is my critical value, the CDF is this entire thing. What is the area under the curve? It's 95%, right? So here's 95%. So it means that it's equal to 1 minus alpha. What is alpha? So 1 minus 5%. So alpha is 5%. So we're going to calculate alpha like this. Sorry, the critical value. Because I have alpha, then it's say alpha is 5%. I plug it. Oh, I keep writing it wrong. So it's 5%. I plug it here. So here I have 0.95. Then I calculate the CDF, the area to the left of that 0.95. How do we do it in R? Very simple. So we have to use that Q function. Do you remember we have Q function, T and P? For CDF we use P, for quantile we use Q. So we use Q, the distribution T, and then your significance level or the area to the left is 0.95. And so for T distribution I need to put the degree of freedom as well, n minus k minus 1. So if you go ahead and type this thing in R, I want you to give it a try. 0.95, and the degree of freedom here in this example is 28. This example comes from the textbook. If you use 28, you will get, please give it a try at home. You will get this 1.701. So this is your critical value. Then you have everything. You have alpha, you have t, you have critical value. Your last job is to compare the critical value with the tested statistic. If your tested statistic is large enough, larger than the critical value, you reject the null under that significance level. Okay. Now let's go back. We're ready to go back to our original example, wage versus education. See, so here this was our example, right? Wage versus education. And we were interested to see if this holds or not. So if this beta experience is greater than 0 or not. So actually, you know what, because you have the video, you can rewatch this thing. So let me erase something here. Let me calculate it for you. Let's calculate this t-stat. I'm gonna do this, go over the steps one by one and review it for you one more time very quickly. Imagine this is my hypothesis, right? If beta experience is greater than 0. So when I look at this one, I realize that we're talking about one tail. So this is the way that you should approach one tail tests. And it's a very good idea to quickly draw something like this for yourself. Do something like this. And this shaded area is going to be your significance level, 5%. Okay. Imagine we're going to report numbers for 1%, 5%, and 10%. Okay. So this is then your first job is to calculate the t-stat. What is t-stat? It's your coefficient, beta hat experience, which is 0.0041 minus the population parameter under the null, which is 0, divided by standard error, 0.0017. See, it's very straightforward, very simple, straightforward. You have two numbers, you divide them by each other, as long as this is 0. Okay, so you will go ahead and calculate this number. This is what we're going to do in the next slide. And then, so let's say number 1, number 2, your significance level, number 3, calculate the critical value. How we do that? It's going to be quantile t-distribution, 95%, because we're talking about this guy, critical value. And what is the degree of freedom? N minus k minus 1. So what is your n? 526. So 526 minus k. What is k? A number of explanatory variable. Education, experience, tenure. 1, 2, 3. So minus 3 minus 1. So if you go ahead and calculate and type this thing in R, you'll get a number. And then step 4, compare your t-stat with that number that you had with your critical value. If it is greater, you reject. If it is less, you fail to reject. Okay, hopefully that was a quick review of what you're expected to do for the homeworks and exams and things like that. Now let's see what do we have on this slide. Okay, so this is what I already wrote down there. T-stat for the experience, 0.0041 divided by 0.0017. It's roughly 2.41. So this is my t-stat, number 1. And then in order to calculate the critical value, I have to calculate the degree of freedom. It was 522. We already talked about this one as well. And then these are my significance levels. So we're going to look at 5% and 1%. So 1% is more conservative. So critical value for 5% is 1.645. And again, quickly, I want you to confirm this in R for yourself. So here is 5%. If I want to calculate this number, it's going to be QT 95, and what is the degree of freedom? 522. Give it a try. You should get 1.645. And now let me use another color to tell you 1%. So let's say here is 1%. So 1%. Then what is this number? I'm going to write it up here. C is equal to, we showed C 0.01. QT, what should I put here? 99% because it's 1 minus alpha, and then the degree of freedom 522. And if you do the math, you will get, actually if you type it in R, you will get 2.32. We're done. So we have our t-stat, we have a couple of critical values. Then we're going to compare the t-stat with the critical value. Look at that. The t-stat is 2.4. And it's greater than 1% significant level critical value, which is 2.32, and greater than 1.645. So in either case, we are going to reject the null. So we reject the null. What was null? Null was that experience is irrelevant. So we are happy, we reject that. So if I reject the null, I get the alternative. What was alternative? Experience had a positive effect on wage. Okay, so overall, you're happy with this regression analysis that you're doing. Why? Because it says that at 1% significant level and at 1% significant level, even if you're super conservative with 1%, we can still reject the null. We can still say that we reject the idea that experience is irrelevant, and we get the alternative. Alternative was education had a positive effect on wage. So the null hypothesis is rejected because the t-stat exceeds the critical values. The effect of experience on hourly wage is statistically greater than 0 at 5% and at 1% significance level. So here's an intuitive question for you. If I tell you that I can reject the null at 1%, can I say that I can reject without doing any calculation? Can I say that I can reject it at 5%? Can I say I can reject it at 2%, at 3%? The answer is yes. So if you can reject the null at 1%, it means that you can reject it at any number greater than 1%. However, if I can reject the null at 10%, I cannot say that if I can reject it for 1% or 5%. You cannot go the other way around, right? All right, so that was a one-tailed test example. Let's look another one-tailed test example. So this time, we're going to look at the left tail. So we covered the right tail. Now let's look at the left tail example from the textbook. So here's the example. We want to test, well, first let me read the equation for you. We are regressing mathematics grade on, and this is total, let me see, total controlling for staff and total, I think this is total compensation of the staff. And this is the staff number, and this is the number of students enrolled in the class. Okay, so we are doing this regression, and we want to see if the school size, a smaller school size, leads to better student performance, right? So if you think about the public school versus private school, maybe public schools, the classes are, I don't know, 30, 40 students. In public schools, the classes are 5, 6, 10 students, right? We want to do a study that if the smaller school size will lead to a better performance, in this case, in their math grade, math score grade 10, okay? After controlling for number of staff and total compensation for the faculty. Okay, so what I want to show that if this beta of enroll is less than 0. Why less than 0? Because I want to say that if the school size is smaller, the performance is higher. So I'm looking for a negative relationship between number of enrollment or people in the classroom versus the math grade. So that's why I'm interested to do if it is less than 0 or not. So if this is my alternative, what is null? It's going to be beta enroll greater than or equal to 0, right? Again, the textbook tend to use 0, look at only the one equal to 0 or not, but nothing is wrong with doing it this way. All right, again, guys, I want you to pay very good attention. I know I'm repeating myself, but I think repetition makes perfect, right? In one sample, I already know that the sign is negative. In one sample, you already know the answer. What you're interested in is to make some inference, make some statement about the entire population. For that, you have to construct t-stat, you have to compare it with your critical value, and then you make statements. Okay, so let's do that. So what is your t-stat? So our t-stat is going to be, so these are the steps. Step number 1, calculate the t-stat. The t-stat is going to be, look at that, I have my coefficient, it's minus 0.0002 minus the population parameter under the null, which is 0, divided by standard error, 0.00022. So this is going to be my t-stat, okay? I think, actually, let me cheat a little bit and see what is the answer. The answer is going to be minus 0.9591. Okay, so here is minus 0.91. Step number 1. Step number 2, what is your tolerance level? So let's say my tolerance level is 1% or 10%. We're going to look at different numbers. And for that, you can quickly plot this distribution, and it is left-tailed, so we are interested in this. So let's say this is 10%. I have to calculate the critical value corresponding to 10%, and I have to calculate the critical value corresponding to 1% or 5% or 15%. I think in this example we're going to do 1 and 15%. But that's the idea of what we're doing. So let's say 10% is green. I'm going to do 1% in red. Okay, then calculate the critical values using R, Then you have to compare your t-stat with the critical value. So compare t with the critical value. Okay, so here your t-stat is negative, your critical value is going to be also negative. So I encourage you to compare the absolute values with each other. So if the absolute value of t-stat is greater than critical value, absolute value of the critical value, go ahead and reject the null. Otherwise, you fail to reject. So here's reject. So let's, again, as a previous example, let's look at a general case, and then we'll come back to this example. So this is a general case for testing against one-sided alternative. Now let's figure out the left-tailed test. So here's our beta j is less than or equal to 0. That's why it is left-tailed. And we reject the null if our tested statistic is too small. How do we define the too small? We have to compare it with the critical value. How can we get the critical value? We have to set the significance level. And after, let's say if the significance level is 5%, we can use this. We know that this is t-distribution. we have the degree of freedom, which is 18 there, and we can back out this number. So how do we do it in R? So in this example, it's going to be QT. Okay, so what should I use here? Should I use 95% or 0.5? So what do you think? Here, we're going to use alpha, right? And alpha is going to be 5%. Because remember, this is the area to the left and the degree of freedom. Okay, so if you plug these numbers in R, it is 18. If you just type QT, open close parent, 0.05 and 18, you will get minus 1.734. And at the end of the day, the rejection rule, this is the way that the textbook is writing it. But again, I want you, it's going to be a better idea to always compare the absolute values. If the absolute value of your tested statistic is greater than the absolute value of the critical value, either for left tail or right tail, so this is a good news. For left and right, look at the absolute numbers. If it is greater than, good news, reject the null. Let's go back to our example. We already calculated this number. We know what is the degree of freedom, it's 404. And we calculate the critical value for 5%, critical value for 15%, minus 1.65, minus 1.04. I want you to give it a try and back out these numbers in R. In R. You should know how to do that. Okay, now look at that. You are going to compare this number, the absolute value of this number, with these two numbers. So what is my t-stat? The absolute value is going to be 0.91. What is the absolute value of the critical value for 5%? It's 1.65. Critical value for 15%, it's 1.04. In either case, look at that. Our t-stat is less than both of them. So it's bad news. So bad news, it means that we fail to reject the null both at 5% and 15%. So this is bad news. If I fail to reject the null, so we fail to reject the null at both of them. So what can we conclude? The null hypothesis is not rejected. We fail to reject because the t-stat is not smaller than the critical value. Again, if you're looking at the absolute value, it's not larger than the critical value, right? This implies that we cannot reject the null hypothesis that there is no effect of school size on student performance, not even for a large significance as 15%. So going back to our equation. So what was our interesting research question? We thought that we were interested to see if in the entire population, the number of enrollment has negative correlation with the math grade, student performance. In one sample, that was the case, but in the entire population, we cannot conclude that. Does that make sense? Why do you think that's the case? Look at the standard deviation. Standard deviation is large, so 0.0002 versus 0.00022. So it means that only one standard deviation from this number, it's going to change the sign completely. One standard deviation above that number, it's a positive number. One standard deviation below that number, it's a negative number. So your story is completely changing sign if you work maybe with another sample, or another sample, or another sample. So that's why we say that, you know, this is not significant. So we fit it at what percent? At both at 5% and 15%. Okay. What about 1%? If you fail to reject it at 5%, what does it imply? It also implies that you fail to reject it at 1% because it's, if anything, 1% is more conservative, right? Okay. So I think that's pretty much it about the one-tail test. Now let's quickly do the two-tail test and wrap up the discussion for this this session. I know it's becoming a long one, but the majority of it was just repetition from our statistic course. But hopefully I was able to connect the dots of why are we doing this and why we needed to make that assumption number 6. So the two-sided alternative is if you want to test if a coefficient is relevant or not, if it is not equal to 0. Okay, we're going to reject the null in favor of the alternative if your statistic is too large. What does too large means? I have to look at the significance level. And when I have the significance level, I have to calculate the critical values. How do I calculate the critical values? Like this. If your alpha is 5%, then it means that it is a two-tailed test. I have 2.5% on the right, 2.5% on the left. Then you can go ahead and calculate this critical value or this one. Really, it really doesn't matter. You know, remember in normal distribution, we did this exercise a lot. You know that it's symmetric. You know, if you calculate one, you can get the other one, and etc. So let's say, I don't know, I'll do this one. I want you to go ahead and give it a try to calculate this one. So how do I calculate this one? It's going to be QT. What is the probability to the left of it? 975, right? Because it's 1 minus alpha over 2. So this is alpha over 2, 1 minus alpha over 2, right? And the degree of freedom, in this example, degree of freedom is 25. If you type this thing in R, you will get 2.06. Please give it a try. And again, this is our general rule for rejections. Absolute value of the T statistic is going to be, if it is larger than the absolute value of the critical value, we are happy. Okay, happy means that we reject the null, we get the alternative. Now let's look at an example from the textbook. And for this one, we're not going to calculate things manually. Because, okay, this is the time. For one-tailed tests, we have to do the calculations manually, especially when it comes to the significancy, because we're dealing with alphas. Okay. For two-tailed tests, the output of the R that you get from the summary, so if you use the summary function, so simply look at that. We're regressing college GPA and high school GPA and ACT and the skipped number of the skipped classes. And the default output that comes with a summary function is going to calculate, so this is your model MRM, is going to calculate everything you need. So it's going to calculate the t-values, and next class we're going to talk about the p-values, right? So look at that. So for instance, the p-value, the t-value for high school GPA is 4.39. The t-value for skip is minus 3.197. And you can confirm it by calculating it manually. So for instance, let's do it for skipped. So what is the t-value? T-value for skipped. It's going to be minus 0.083 minus 0. If you're testing it against 0, divided by 0.026. If you do the math, you will get this minus 3.197. But automatically, you can read these numbers from the table, from the output table. And okay, but the nice thing about this output table is that there is this number of stars here that you can use. So for instance, if there are in the summary output, if there are 2 stars, means that it is significance at 1%. If there are, 2 star, 1%, 5%. Yeah. Well, I think this is between 0 and 0.001. Between let me actually pause for a second and give you a better explanation. Okay. So 3 stars means that it is significance at 0.001, so it's 0.1%. Okay, 2 star means that significance at 1%, 1 star significance at 5%, 1 dot significance at 10%, and etc. Right? So for instance, if you see 3 stars, it's super significant. It's significant at alpha is equal to 0.1%. This is not significant. This is significant. There are 2 stars, alpha at 1%. Okay, so this is the output for the summary, and let's actually quickly interpret these things. So we want to say, at the end of the day, we want to see if high school GPA, ACT, and number of skipped classes is relevant or not. So what does the model imply? The model says that, well, we don't care about the. Let me actually erase everything. We don't care about the intercept, so we don't care about this part. So let's see if high school GPA, you're reading the output from the R, right? High school GPA, the t-set is large. If you compare it to the critical value, it's done in R, and you say there are 3 stars, so high school GPA is super significant. The number of skipped classes, look at this one. Again, the t-value is large, the absolute version is large, and it is significant at 1%. Okay, so it seems that the number of skipped classes and high school GPA are significant in terms of explaining the college GPA. So it means that higher high school GPA is related to higher college GPA. The more number of classes you skipped is negatively related to your college GPA. However, for the ACT, look at the ACT score. It seems that ACT has a small t-value and it is not significant. So ACT turns out to be not significant. So this is the bullet points that we're putting here. The effect of high school and number of skipped classes are significantly different from 0 at 1% significance level. Very good news. Because remember, in the entire population, now we can make statement. However, the ACT is not significantly different from 0, not even at the 10% significance level. Okay. All right, so let's see what we have. So the rest of it is pretty straightforward. Let me back out a little bit and talk about this thing that we have in R. This is the thing that I don't want to say don't like, but it is inconsistent. The author of the package, I don't know why they didn't fix it. Maybe there's a big fixed cost now if they want to do it, but when it comes to explaining it to students, it makes them confused. So let me try to clear it out right now. You know, you can look at the output in R. In the class, I'm going to show it to you, but let's talk about it here. You know, you can look at the output if you use the summary versus a stargazer. Okay. If you use the stargazer output, then the number of stars are different there. So 3 stars is 1% significant level, 2 stars is 5%, and one star is 10%. So this is more standard. So if you read the papers, if in the table of the output in the paper there are 3 stars, means that 1%, 2 stars means 5%, 1 star 10%. However, in the summary output, you see that 3 stars is 0.1%, 2 stars 1%, 1 star 5%, and a dot 10%. So you see the difference. So for the summary, 3 stars. So this is the stargazer output. Let me use consistent color. For the summary output, 3 stars is 5%. Sorry, 3 stars is 0.1%. 2 stars is 1%. 1 star is 5%, and a dot is 10%. Okay. Depending on which one you want to go with, most probably for many of the homeworks, you're going to go with the summary output because the t-stat is going to be automatically calculated. And the stargazer output, you have to calculate it manually. So it's your choice. You know, you can practice it, but the more you practice it, the easier it becomes. So let's quickly go over the very final slides. What are these things? It says that if a regression coefficient is different from 0 in a two-sided test, we say the corresponding variable is statistically significant. So whenever you hear me says that, or other people says that, is your coefficient statistically significant? This is what they mean. Is a two-tail? Can you reject the two-tail test? Okay. And then there are some rule of thumbs. You don't need to memorize them, but the more you practice them, the easier it becomes. So it says that if your sample size is large enough, right, you don't need to, you know, calculate the critical values and etc. If the sample size is large enough, and then you look at your t-stat. If t-stat is greater than 1.65, you know, your coefficient is statistically significant at 10%. If it is greater than 1.96, 5%, 2.57, 1%. Where are these numbers coming from? You remember the rule of thumbs from normal distribution? So we had these things before. So I think so this was the 1 standard deviation, 2 standard deviation, 3 standard deviation. Sorry. 90%, 95%, 99%. So these are 1%, 5%, 10%. So the rule of thumbs, well, we had here for two-tailed, we have, I don't know, 1.65, 1.96. Again, you don't need to memorize them. You know, generally, if you look at the t-stat, if it is greater than 3, it's awesome. It is really large. You can reject it all. Sometimes even t greater than 2 is enough because we know that it is at 5% significant. But that depends on the tolerance of the researcher. Okay. Okay. So the last couple of slides, this should be also easy. So let me pause here and see. It's 44 minutes. So this one become a long one. So I'm gonna do the last one in a 5-minute, in a shorter video, and then we will call it a day. So I'll make sure that the next video for the week is going to be less than an hour, 15 minutes. So don't worry. I have to see what is the duration of this one.